Okay, right. What we will also look at now is what we call snubbers in the context of the fact that snubbers are used to limit transients. Okay. Now, when we refer to transients, we are referring to dv as a function of dt and di as a function of dt. Okay. The circuits that are used to limit these transients, dv dt and di dt, are called snubbers. Okay, simply meaning they limit transients. Okay, since they delay the rise of device current or voltage, to limit the voltage rise rate, a capacitor is placed parallel to the device. An inductor in series with the device limits the rate of rise of the current in the device. Now, how does it do this? It does this now because remember, normally when you have, let's say for instance, an inductor, what's happening in an inductor is, in an inductor, voltage is leading current, simply meaning current is lagging voltage. Now, what does that mean? The reason why current is lagging voltage is because the current has to remain behind, sort of. Obviously, this is now anecdotal. It's an analogy, right? The current has to stay behind. Why? Because it's responsible to first generate a magnetic field up until that magnetic field reaches a point where it reaches saturation. Okay? So the same thing happens in a capacitor. In a capacitor, you have voltage, you have current. Here's the thing. Your current, it's leading your voltage. Your voltage is lagging your current. Simply meaning voltage is the thing that stays behind in a capacitor. Why is that the case? That is the case because reason being your capacitor, it has to build up what we call an electrostatic field. In order to generate or to build up that electrostatic field, it requires, for now, let's call it a potential difference. You can call it a voltage, but I'll for now call it a potential difference, okay? And then the potential difference, it will take a unit of time for it to build up the electrostatic field to the point of saturation. Okay, now how does that link into snubbers? It links into snubbers in the sense where, let's assume there's an instantaneous change in current in a circuit. Let's assume you have a diode in that circuit. What will the function of the diode be? The function of the diode will be to resist that instantaneous change in current, simply meaning it will delay the rate at which the current is changing in the circuit. Okay, the same thing happens with the capacitor. What does a capacitor do? A capacitor, it will delay the rate at which there's an instantaneous change in voltage, simply meaning if you have voltage acting in a sporadic sense, that sporadic sense, in whatever way you deem it to be, it will be delayed, meaning there's an inherent buffer, voltage buffer built into it that will delay the movement of voltage, if I may call it as such, or the application of voltage. Okay, so that is essentially where the snubber technology fits into play. It's to limit voltage rise rate. A capacitor is placed parallel to the device. Okay, if you want to limit the voltage rise rate, you place the capacitor parallel to the device. An inductor in series with the device limits the rate of rise of the current in the device. That is exactly what I said just now. Okay, now we are going to look at the classification of snubbers. Snubbers may be dissipative or non-dissipative. Okay, the energy used to effect the action of snubbing is lost in dissipative snubbers. Non-dissipative snubbers return the energy to the circuit when the snubbing action has been performed. Dissipative snubbers limit the rise of voltage and are classified as being polarized, reverse polarized, or unpolarized. Unpolarized snubbers are used with bidirectional devices. Okay, now we are going to look at 2.3.2, wave shaping by using snubbers. If snubbers are not used, okay, the voltage over a device will vary, simply meaning it will rise very rapidly during turn off, And during turn on, the current will rise very rapidly, as shown in figure 2.1. Okay. The same components that limit the rate of rise of current or voltage can be used to shape one of the two components that determine the power dissipated during the switching process. This allows for a reduction in the power lost during the switching action. For instance, if the current can be kept low until the voltage has fallen to a low value, then the product of V and I will be like a fraction of which it would have been. Okay? The same can be said that if the voltage can be kept low until the current has fallen to a low value, the VI product will be a fraction of what it would have been if left unaltered. Compare the wave shapes in 2.1 with those in figure 2.2, and then what do you notice? Let's just see. This is 2.1. Okay. Figure 2.2. Okay, right. We'll get there.